Hello, welcome to PhyzQuest. So this is the video solution for CSIR NET December 2019 Part C, question number 12. The question is, the wave function of a particle of mass m constrained to move on a circle of unit radius centered at the origin in the xy plane. And the wave function is described as psi is equal to a cos square phi, where phi is the azimuthal angle. We need to find out the possible outcomes of the measurement of z components of the angular momentum Lz in the units of h cross. So basically you are given a wave function and you need to find out the possible eigenvalues of the Lz operator in the units of h cross. So let's get started. So this question comes from the section quantum mechanics, and the concept involved here is hydrogen atom. Now why I said hydrogen atom? Because there is nothing is mentioned there. It's about only a particle of certain mass. So why I said this is about hydrogen atom? There are three reasons. First of all, the question mentions about a particle moving in a circle around origin, which is very much similar to the hydrogen atom, where the electron moves around the nucleus. Second is, the wave function here is expressed in terms of polar coordinates. See here, this is polar coordinates, and in hydrogen atom, in the case of hydrogen atom, the wave function is expressed in terms of spherical polar coordinates. And the last reason which confirms it is the mention of the z component of the angular momentum operator Lz, as quantization of the angular momentum comes into picture while studying the quantum mechanics of the hydrogen atom. So all these three reasons confirms that this system, the given system, is very much similar to the case of hydrogen atom. Now as we have understood, hydrogen atom, the wave function is expressed in terms of spherical polar coordinates. So in order to understand the wave function given in the question, we have to first of all understand what is a spherical coordinate system. See, if this is your Cartesian coordinate system x, y and z. Spherical coordinate system, there are also three variables. They are mentioned as r, theta and phi. So suppose, suppose the case of hydrogen atom itself. Suppose the nucleus is at origin and the electron is at a certain distance r. So this r is the radius of the sphere. Then second variable, which is theta. Theta is the angle between the projection of the r on xy plane and the positive x-axis. And lastly, the angle phi is the angle between r and the positive z-axis. So these are the three variables which are used to describe a spherical polar coordinates, and in case of hydrogen atom. In our system, in our case here, the particle is moving on a circle around the origin in xy plane, and it is making actually a conical shape following an angle phi with the z-axis. So now in our case here, the hydrogen atom wave function is given as psi is equal to r, theta and phi. So here capital R is a function of r, capital theta is a function of theta, and capital phi is the function of phi. And here NLM are the quantum numbers. So here this is the general wave function of a hydrogen atom. So here out of these three cases, here r is said to be the radial part, and the product of theta and phi are said to be the angular part. Now out of these three variables, this phi part is said to be a in e to the power plus minus I m phi, where m is the value is m between minus L to plus L. So now here this is the general format, and we are concerned about this expression of phi only because our given wave function is in terms of phi, that is a cos square phi. So in order to find out, our purpose is in order to calculate the eigenvalues of Lz, we must know this quantum number m. so which we can use to find out the eigenvalue. So what we have to do is we have to convert it in terms of exponential function so that we can compare it with this general term and can calculate the quantum number m. So as per the trigonometry, cos phi is e to the power I phi plus e to the power minus I phi divided by 2. So if we use this formula in the wave function of psi, so then we can write it as psi is equal to a e to the power I phi plus e to the power minus I phi whole square whole divided by 4. So if we expand it, this will be equal to a by 4 e to the power 2I phi plus e to the power minus 2I phi plus 2. So here each of them signify, see, our purpose is to find out the possible outcomes of the operator LZ. So for that we need to understand what are the possible values of m here. So now if we compare with the general expression of phi, that is a e to the power im phi, this will be, in the first case, m is 2, therefore the wave function is psi nl2. Now here we don't know what are the values of n and l, we only know the value of m, which is 2 here. So for the first case the wave function is psi nl2. For the second term, here m is minus 2, so wave function is psi nl minus 2, and the last term is 2, that means 2 e to the power 0, that means m is equal to 0, therefore the wave function is psi nl0. So these are the three possible wave function. Now we will operate it on the z component of the angular momentum operator, and we will find out the eigenvalue. So here Lz psi nlm is equal to mh cross psi nlm. So here mh cross is the eigenvalue we'll get when we operate the angular momentum operator, z component of the angular momentum operator, over a general wave function of the hydrogen atom. So here in our case we have got three possible wave function. So when we operate the z component of angular momentum operator, these are the possible eigenvalues we'll get, that is 2h cross minus 2h cross 0h cross. So therefore the eigenvalues are, in terms of the units of h cross, are plus minus 2 and 0. Now if you check the option here, you can see that option D is matching with our result. So correct answer for this question is option D.